Can we set it up so
Mhm.
that like new participants are always non-video or something? Is there a way to do that?
Mm.
Pedro.
I assume, Ben, you're pointing at Pedro. I can't talk for him. Don't
Yeah, I
worry.
am. Yeah.
I'm doing my best here, but I'm not sure.
Okay, well, I just keep an eye on it, and if anything,
There's a way to do that. So you can set up so that there are specific presenters in a Zoom meeting, and they're the only ones that can do video and stuff.
I know you can do that with panels. I didn't know you could, like, which is like, or webinars, which is a different feature.
Yeah.
Oh, gotcha. I don't know why we don't do that.
It costs even more than like the regular institutional thing, so that's why.
That's
we ran into that when we were setting up PLMW back in June.
Gotcha. Also, Ben, did you accuse me of Zoom bombing?
I just said that it could happen.
Yep.
But we're definitely going to accuse you of it. It's definitely your fault.
Well, yeah. I mean, if anyone was going to do it, it would be me, 100%.
That's all I was saying.
I'll own that reputation.
You're out in California, right?
Yep. You're in Palo Alto, where the air is finally breathable.
Well, that's good.
Yep.
ATR.
Okay, I've made all the professor co-hosts, so if anyone needs to be taken care of, you guys have to help me out. So as I was talking with Ben, my plans for the future is to just make the YouTube link available. So then we get, I don't know if we're gonna have any problems today, but like since it's open to the broader public, we might get someone just like some troll or something that we have to take care of. But in the future, if we just make available the YouTube links, then that wouldn't be an issue. And then we can make questions through Slido or something, and only the organizers come to the channel.
Yeah.
But I'm going to work with that with Krish the next week, and let's see how that goes. But for now, I think we're good. We are live on YouTube. I'm going to send the link on chat in case anyone want to share, or I don't know. The good thing about the being live on YouTube is that the video is gonna stay there on PurPL channel right afterwards. So then I'll just rename to with the actual title of everything and date. But I think we are good to start now.
Okay. Yeah, let's get started. Because as we mentioned earlier, it's quite late for Ilya. So it's my great honor, yes, it is an honor to be hosting Ilya at our PurPL Seminar this week. So I've known Ilya for quite a while now. He's currently a tenure-track faculty, associate professor at the Yale NUS College in Singapore. Before he joined Yale NUS, he lived all over Europe. He was faculty at UCL, I guess, for 3 years. He did a postdoc at MDIA in Spain. Before that, he got his PhD at KU Leuven. I hope I said that right. And I believe you did your bachelor's in Russia, yeah? In Petersburg. Okay. Yep, right. So he's been everywhere. He's lived all over the world, and his research is broadly in the design and implementation of programming languages, but his contributions and his interests have been as varied, like inside that broad domain, as the places he's lived. So in particular interest for this month, he's done a lot of amazing work in the verification of distributed and concurrent programs and protocols. He's developed and applied separation logics for fine-grained concurrent programs and data structures. In fact, he's such an expert that he created this beautiful chart that's a family tree of concurrent separation logics that has, I don't know, like tens of entries, like maybe 50 or plus, that charts out the history of these divergent logics in the field. He's also worked, on static race detection, abstract interpretation, and synthesis of heat manipulating programs. That synthesis work actually won a PurPL 2019 Distinguished Paper Award last year. And in fact, in recognition of all of his accomplishments, Ilya was the recipient of the Ito Dahl Nygaard Junior Prize last year, which is just an amazing honor and very well deserved. His more recent work has been applying the ideas of concurrent object verification to reasoning about smart contracts, Ethereum bytecode, and blockchain consensus. Although we won't mention blockchain too much, hopefully, from now on. having said that, he's the designer and the co-developer of Scilla, which is a programming language for smart and safe and secure smart contracts. And he's an advisor to Zilliqa, which is works in blockchain as well. So today's talk, he's going to be actually talking about how he can use static analysis to more efficiently and correctly distribute validators of concurrent blockchain transactions in a way that significantly increases transaction processing throughput for real-world smart contracts. So it's a real, I think it's a real nice application of sort of formal methods to a real-world problem. And with that, I could go on and on about how great Ilya is, but I think let's hear what he's been working on. Thank you, Ilya.
Thank you so much, Ben. Before I begin, I want to say how happy I am to have spent these my evenings talking to various folks from PurPL. It really has been a blast. I enjoyed every single meeting, and it was really great to see so much perspective on different aspects, pretty much all of which I'm very much interested in: systems, synthesis, PL design, verification, and the others. So hopefully I'll get something to share with you that you also might find useful. And with that, I'm going to share my screen. Hopefully it works out well. Okay, so can you see the first slide? Yes. Okay, now the more tricky question, can you see the slides switching back and forth as I'm doing this? Great, okay. So we are all set then. And with that, I will begin. All right, so the talk is going to be on the tool called CoSplit, which is an application of a static program analysis technique for sharding of blockchain smart contracts, whatever it is. So first and the most important, this is obviously joint work with George Perler, who is the superstar first-year PhD student at NUS School of Computing, working with me, and also with Amrit Kumar, who is a cryptography expert and currently president of Zilliqa, which is the blockchain startup hosted in Singapore. So to give you some idea of what we are going to work on, we have a problem and we have a technique. So, and the problem is making smart contracts shardable. And if you are unfamiliar with what it is, that's going to be explained on the next slide. But this is a problem that comes from a domain external to programming languages. It comes from distributed systems and security. But the technique that we are going to apply is very much in the field of classical PL, which is static program analysis and abstract interpretation. So sharding, as it happens to be, is a technique that is mostly pioneered by databases. And this is a technique that allows to scale more than distributed protocols and specifically blockchains. And the problem that we are going to address is how to apply this technique to scale blockchains, specifically that support smart contracts. And by smart contracts, I mean user-defined replicated computations that typically manage some shared state. And that's something that we are going to do with the help of static program analysis. So the problem is, well, blockchains don't scale. And well, this is something that I'm going to spend a little bit of time elaborating upon. And by all means, I invite you to interrupt me at any point because interactive talks are much more fun, and it's good if we are all staying on the same page. So here's an illustration of why exactly blockchain protocols don't scale. And obviously, I'll be greatly simplifying many things, and that's the reason why I invite you to interrupt me. But roughly what we have is we have a distributed network of nodes. Each node can be called a validator or a miner. And these nodes collectively store the same replicated state, which is what we're going to call the blockchain state. So the state is arranged as a chain of blocks or a ledger, but this is kind of irrelevant. So what this blockchain state can be? Well, it can be thought of as a collection of stateful objects, each of which has, well, a state, and also has some interface to operate upon. So like keeping it within the domain of interest of those systems, the objects might be something as simple as a simple shared counter that just stores a single field of the type unsigned integer 128-bit depth and a single method to increment it. We can also have something more practical like an object, a contract that implements a fungible token, essentially mini bank, allowing one to transfer money between the entities and also approve the transfers made by some trust party. And we can also have something as exotic as the registry domain, which actually not exotic at all because that has been one of the most lucrative applications of the technology. And these contracts are very, very common. So how do users interact with this thing? So users, they might be the users that host those nodes themselves, or they might be external clients. And with third-party software, they emit transactions that go into this network of nodes. And through this network of nodes, these transactions alter the state of the shared smart contract. So for example, here we have 3 transactions, one going to the fungible token, another going to the counter, and the third one going to the domains, and each one of them tells what is there to be done. So these transactions all collectively go through the same network of nodes. And once the nodes decide that those transactions are good, they do not violate the state and they can proceed, they are being applied to those contracts, and the contracts are being executed, the state is being updated, and this state is then replicated in all the nodes. So this is essentially a 101 of blockchains, and there's nothing more specific about them. Okay, so and then the state advances. So typically that's what happens in blocks, hence that. So we came from block 0 to block 1. So now the problem happens. What's going to be if we actually have too many transactions? Well, they're going to be exactly the same procedure that follows. Even if we have more transactions, they're still going to go through the very same set of nodes, essentially all the nodes in the system, that each of the nodes individually validate, and then will give a green light in the case of the transactions being valid to proceed to the network. And at this point, you can probably start seeing the problem. So essentially, this is a replicated distributed system, and the work is being replicated, and there is really no benefit of having more nodes in it. So because the nodes have limited computing power, and they also can hit the bandwidth limitations. And if you think, oh, but well, shouldn't be able to get a more performant system if you add more nodes, and the answer to that is no. Actually, blockchains are such a perverted case of consensus systems that they become slower if you add more nodes, because now all those nodes need to provide the validation, and they also need to synchronize with each other. Okay, and this is a problem. So we have this ginormous execution bottleneck. So obviously transactions multiply, and we still need to process all of them. Nodes have limited bandwidth and limited processing power. Okay, so how can we solve? Well, the idea is actually pretty simple, and it comes from databases, which like pretty much every single interesting idea in the systems community always comes from databases. So instead of thinking of the network of nodes as this monolithic construct which needs to repeat the same work regardless of the identity of the node, let's logically partition this set of the nodes into independent subsets. And this is what's called shards. And now we are going to make each shard responsible for managing a disjoint component of our replicated state. So here, for example, the shard 1 is going to be responsible for working with the first contract, and the shard 2 is going to be working with the second contract, and shard 3 is going to be working with the third contract, under assumption that these contracts actually do not talk each other, so there is no communication. So this is actually something that can be enforced. And now if we look at the transactions, well, that's essentially how they're going to go. So naturally, we have a parallel speedup, and the throughput should increase proportionally to how many shards we have. Actually, the whole idea works beautifully, even not for smart contracts, but for the simplest kind of these protocols that only have one kind of transaction, namely transferring funds from one party to another. But why exactly did it work so well, I will explain just in a couple of slides. So this idea of having the state disjoint and manage it disjointly and only exchanging the snapshots for the parts that the shard is not managing is very simple, but obviously it has its limitations. And specifically, the limitations become particularly apparent when we have very popular smart contracts. So let's revise the same example. So out of this three, fungible token is by far the most popular contract in Ethereum. So in Ethereum standard, it's known as ERC20, and this is the contract that people use to implement a mini bank or a mini crowdfunding campaign, which you can use to manage tokens for your own purpose, and people can pay you money, and then they can have a share. And this is something that this contract implements. So popular fungible tokens for projects that are overhyped on the internet, they become bottlenecks of the execution. So what happens is that there are way more transactions come into these popular contracts than to any others. And even though we relieved the entire network from the duty of processing these transactions altogether, still we have a shard-2, which is going to carry all this load of validating this set of transactions that dedicated to the second kind of contract. And this is clearly a problem. So when you have popular smart contracts, turns out the sharded blockchains have the same kind of throughput scalability problem as normal blockchains do. And if you think it's an artificial problem, well, it's not, because there are contracts like CryptoKitties or very popular ERCs in Ethereum that clog the network, and for minutes or hours, people couldn't actually get any other transaction processed because the transactions to those popular contracts were lined up. Okay, so what are we going to do about it? Well, and in fact, the solution is kind of already on the surface. So we already have this nice modicum of disjointness when we partitioned the set of the different disjoint contracts with disjoint state to be processed by different shards. So can we, in fact, zoom in on a single contract, let's say this fungible token, which is the perpetrator in this particular case, and try to see if there is any inherent disjointness in it, and can we exploit this disjointness for the sake of having the same nice parallelism as we can have with sharding contracts that are probably different from each other. So the very high level.
Ilya,
Yes.
I have a question before you move on.
Sure.
Just maybe you can go to the previous slide.
Yep.
Yeah. So firstly, how easy it is to determine this independence or disjointness of contracts, and what exactly happens to contracts that have dependencies. And the second question is, does this kind of parallelization still provide the same cryptographic guarantees as one would get?
Okay, good point. So two questions. Okay, first, how easily we can determine the disjointness of the contracts themselves, I guess, in terms of their dynamic executions. And the second is, don't we compromise the security guarantees? So answering the first question requires to tell a little bit more about the exact programming model that we use. And I would say that in Ethereum, determining that is not easy at all, because the contracts is one big soup, which essentially like a bunch of objects that can call each other recursively and whatnot. Mm-hmm. So if you have a more restricted model in which each contract doesn't call other contracts, but rather send messages to them, then you can just restrict your transactions that are going to be started to those that promise to make at most one message call to, and that message call should not be to another contract, but rather to a user. And this is something that can be enforced dynamically very easily, but obviously there is a class of transactions that span multiple contracts, and the solution for them is just to have a dedicated shard that processes all of those. And this is more or less how sharding in smart contracts works in the systems like Zilliqa, well, until this work has been introduced. So there was this dedicated shard called directory service for historical reasons that was taking most of the load that had to do with popular smart contracts or multi-contract transactions. So about the security guarantees, that is something that piggybacks on the security guarantees of the original protocol. And well, there are some boundaries on like what should be the number of parties in each shard, and how frequently the view shift needs to change there, because they all use practical Byzantine fault tolerance. And I don't think we introduce any new assumptions or any new constructs on top of that. So the original security guarantees for the system, which has been designed just for peer-to-peer transfers of money, they very much extend to us as well.
Okay, all right, thanks.
Okay, thank you for the question. So let me proceed.
Can I ask one question too?
Yeah.
Yeah, this is probably silly. I'm just interested to know who's responsible for figuring out how to divvy up the contracts, and then also assigning them to distinct shards and like sort of doing all the network setup. Is this
all right? Yes. So there is actually I have a really nice picture down the line, but maybe I should have indeed pushed it earlier. Yes. So there are actually multiple roles the different nodes take in the system, and with certain redundancy, obviously, because that's all Byzantine. setting, there is a set of nodes that perform the dispatch. So the clients, they talk to any of these nodes, and these nodes run very simple logic to determine this transaction based on its inputs and involved parties, which exact shard it would go to. So in the simple peer-to-peer money transfer, the thinking model was that each account which can emit money, it's assigned to one particular shard. And those assignments are being reshuffled every once in a while, every couple of hours, but it's deterministic and it can be determined.
Okay, thanks.
Yeah, my pleasure. So for the context, is based on the identity identifier assigned to the token upon deployment. All right, so the intuition. Blockchain is a state transition system. It's a state replication protocol, and it has a state. And it also has a set of rules that tell how exactly the transactions are being processed. And these rules also say which states are legal. And with this set of rules and this notion of state, people already have come up with the ways to partition the state logically and assign it to different groups of nodes and have strategies for sharding. And certain kinds of transactions are sharded better than the others, but I'm not going to go down this rabbit hole. So for smart contracts, the analogy actually extends quite well. So smart contracts are also, if structured sufficiently well, they are very easily represented as state transition systems that have a state, and they have code that governs how the state evolves and which states are considered legal. So can't we extend the same intuition that is used for sharding state in the vanilla blockchains themselves to shard particularly popular smart contracts? And the top level, the high level questions we are asking is, can we look at the smart contract code and determine whether this code defines a shardable state machine, something that can be run in parallel and still get a consistent state at the end. More general, this is the favorite PL question. Does the code have the property X that I'm interested in? And this is what the whole programming language field is solving. And unless you, even if you don't remember anything from this talk, this is kind of the crucial slide. So it says that we can shard contracts the same way we shard blockchains, and we can use static analysis to look at the contract code to uncover those opportunities. So that was a rather lengthy introduction, and with that, with your permission, I will just restart my talk, reiterating the slide. And the contributions that we make in our talk are of the following kind. So first, we identify mechanism for sharding Ethereum style contracts. And those mechanisms actually based on the ideas that are not particularly new. So the ideas of disjointness, ownership, and also commutativity, which is going to come just in a couple of slides. This is something that people obviously saw in concurrent and distributed systems and even in parallelizing compiler. What we believe is now is that those ideas, they linger around in the smart contracts and they just need to be uncovered somehow. So with that comes our second contribution, which is the static analysis called co-split for commutative splitting. And that's a tool that automatically infers the best strategies to execute smart contracts in parallel. But the catch is that smart contracts need to be written in a special programming language. They're not written in Solidity, they're written in a language called Scala, which, and some of you might be pleased by that fact, is a dialect of ML. So, and this is the language that we use in Zilliqa to write smart contracts. So on the practical side, besides the static analysis, which is nice in itself to have, we have end-to-end integration of this tool with the production-grade sharded blockchain. So the analysis itself doesn't yet run in production, but we ran it on an extensive case study, and it seems to work well. And this is what we have demonstrated by our evaluation, where we took all unique smart contracts that are deployed on Zilliqa by, well, regular folks, regular clients to date, a few dozens of them. I mean, if we consider only the unique ones, and we ran this analysis and we uncovered lots of opportunities for parallelism due to sharding. Okay, so these are the contributions. Now to more specific aspects of what has been done. And the first mechanism that I'm going to show how we leverage for sharding popular smart contracts is exactly what already made an appearance before. This is the disjoint state ownership. So, you know, concurrency is always like has some notion of ownership because the owner is usually the threat or the party that has some exclusive rights to do something with the state. But, and this is how it's determined whether the other parties have a way to manipulate with it. So we already had this modicum of ownership embedded into the splitting the state into 3 separate contracts and giving them to 3 different shards. Now let's see if we can engineer this ownership discipline at the level of individual contracts. So this is a piece of code of the crowdfunding contract that implements the logic of donate transaction. So even though contracts in Scylla, they are somewhat similar to contracts in Solidity, they actually don't have exactly the Solidity execution model. The contracts in Solidity, there are objects that call each other arbitrarily. Contracts in Scylla, there are state transition systems, and there are transitions, not methods. There are event handlers. So that means that transition preserves the atomicity of the contract. It doesn't interrupt midway and calls another contract. The only thing that it can call are pure effect-free functions. So this is a model that we have described in an UPSLA paper last year, also showing what kind of benefits for the perspective, from the perspective of static analysis and verification it provides. And now we are reaping those benefits. So I presume most of you have never seen a Scylla code before. This is roughly what is happening here. So there is some mix of imperative and functional code. For example, imperative code is something that can read the current block number to determine what is the current timestamp that we are operating. And then we can check using some library function whether the current block is smaller than the deadline that's set for the crowdfunding campaign. And if we are indeed in time, so okay, still is a reasonably low level language. So we don't have if, instead we have pattern matching. So if it's indeed the case, then we check if the backer with the identity similar to the sender who invokes this event handler exists. And if it doesn't exist, then we accept the donation and we create an entry for this backer in a dedicated field, which has the type mutable map from the addresses by string of the length 20 to unsigned integers 128-bit length, which corresponds to the representation of money in Scylla. So that's the code. And that code already should give you some idea that it actually doesn't have a very large footprint. So essentially, the only pieces of state that are involved here are, well, this part of the map that is related to sender, and also the max block, which is an immutable parameter. So that's not something that is being changed over the lifetime of the contract. So this very small footprint should sort of hint that this is something that we can probably also use this ownership idea. So instead of having one crowdfunding contract, we are going to have as many copies of the crowdfunding contract that we have, with the catch that shards are going to be to hold ownership over some part of the state that can be manipulated concurrently. So in a way, probably all of you have written a concurrent program of the kind that manipulates with an array using multiple threads. And if you consider these backers to be an array, there is nothing wrong if we split that into disjoint parts and just allow each shard to manage its part, because that is not something that is going to interfere. It's not something that is going to invalidate the other shards logic. So the only tricky bit here is how eventually we reconcile that. So obviously there should be some additional phase in which the shards communicate, but they communicate in a very cheap way without the need to reach the consensus. So going essentially through just one phase. And in this phase, they exchange the deltas for the parts of the array that they do not own, just to keep the up-to-date view. So that was the first mechanism, which is essentially engineering the virtual discipline for ownership. Any questions about this one? Or that's more or less clear? All right, good. The second mechanism, it's slightly more interesting. So commutativity is something that makes an appearance very frequently when we talk in about concurrent execution. So it's something that allows us to cope very efficiently with the non-determinism that we have in concurrent programs. So here's an artificial contract called counter, which has just one mutable field of type integer, which is initially 0. And it has this atomic transition that reads from the counter, increments it by 1, and then stores the new value into the counter. So transitions there are as good as atomic commands, so we shouldn't worry about that being 4 different statements. So that is still executed atomically from the perspective of all other users of the system. Okay, now, why the increment is such a nice contract? Well, because in fact, we can run multiple increments in parallel. And the only things we need to reconcile is to exchange deltas by how much different entities, different shards have incremented the same contract. And there is no way they can conflict with each other if we are careful about our eventual merge strategy. So quite curiously, the idea is that incrementations or any additions of a constant amount compute very well with each other, so there are commutative effects. This is also something that has been exploited in the original design of sharded blockchains that did not consider smart contracts. They only considered those money transfers. Because what is a money transfer? Well, money transfer is essentially decrementing one integer field and incrementing another integer field. They just correspond to different entities. So here, the account A transfers 10 tokens to B and 20 tokens to C. So their balances are being incremented by corresponding amounts, and A's balance is being reduced by 10 or 20. So assuming A has at least 30 tokens to transfer, doesn't really matter in which order these transfers land on the global linearized time scale. And the same thing, it doesn't really matter in which order the transfers of tokens from A to C and to D to C end, because both of them are going to increase the amount of C, and the addition represents the commutative effect. So this idea has been actually put very much to use in the original Zilliqa proposal. So essentially, to make a transfer, a shard needs to own the identity of the account from which the transfer is going to be made, but it doesn't need to own the recipient, because the recipient is going to be the subject of addition, and addition computes, and this is how this whole thing actually shards very beautifully. So the same idea as an increment. So now we are going to leave this transition to the full contracts, but now comes something interesting. So we all know that addition is commutative. So that's something that we have learned in the primary school. But commutative operations do not necessarily yield commutative effects. So here we have two transitions of the same contract, let's say, that both operate on the same field. But one does the increment by a constant, and another doubles. And well, if we start running those transitions in parallel and trying to reconcile them, well, then suddenly it realizes that those two transitions do not commute. So it would be actually not a safe thing, not a deterministic thing, to run these transitions in parallel. Why so? Well, because depending on the order, we can first increment and then double, or we can double and increment. And as we can probably all agree, that doesn't necessarily lead to the same results. So here we, like on the left, we first increment and then double, and right, we first double and then increment. And this is kind of non-determinism due to interleaving of operations processed by parallel shards, something that we want to avoid. So we actually want to have all possible interleavings lead to the same result. So we need to be really careful what actually gives us a commutative effect. And it turns out that adding constants to a single field, that's also commutative. But also multiplying field by constant, it's also commutative. It's just your structure is slightly different. So instead of addition as your operation, you are going to work with multiplication. But here, mixing doubling and addition, that's not going to commute. So how are we going to proceed with this idea? Well, we are going to analyze the code of our contracts with a very cheap analysis based on abstract interpretation. And essentially, we are going to extract the summary of the read-writes effects that the contract performs. Why is it so? Well, if we look at something like the increment, we can see that essentially the only effect of the left transition is reading from the counter and then adding 1 to the value and storing the new value. And there is something interesting. There is this observation that the value of the old counter is used only once. And as long as it is the case, it's actually sufficient to argue for the fact that any number of such transitions run in parallel will commute just because of this linearity. So this idea that certain fields can be used just once and also be subject of certain operations such as addition, that is something that will allow us to judge whether we can make them shardable. So first, this analysis produces the effect summary, something very simple, and it's not yet an indication for whether it's shardable or not. And then this effect summary is going to be post-processed based on what exactly are the parts of the contract, what exactly are the transitions of the contract that we want to run in parallel. And as a result, we will get a number of constraints. So first, let's see how exactly these effect summaries are inferred. Well, here comes a little grammar. I'm not sure if that's very informative at this point, but you can see at the bottom that the effects are actually very simple. So basically it says this transition reads to the field, from the field, it writes to the field certain expression, it accepts the funds, it conditions on certain expression and whatnot. But the abstract expressions right on top of it, they're actually quite interesting. So they not only keep track of the provenance of all the values that participate on them, they also keep track of how many times those values contribute to this expression and what exactly are the operations that are used. And in several lucky cases, this information turns out to be enough to argue about the commutativity. And because we are doing proper abstract interpretation, we also have the top element for the case if we don't really know what is happening there. And in this case, the sharding strategy is going to be very conservative, just put everything into a dedicated shard or anything that doesn't have any commutativity in it. Okay, so here's a transition from the fungible token that transfers an amount of money designated by this parameter called amount to the recipients named 2. So first it reads from the field, from the map balances corresponding to the sender of this transaction. Then it examines the result of that. So it conditions based on whether it's present there, it's some or none. So if it's some, we know that so far the contribution to that variable val was the value of balances of sender, and it contributed just once, so there was no any operation that used this value multiple times, and also there were no any other operations like reading, like addition and multiplication. So things get more interesting. So now we start using that in the condition, also involving other variables. We start subtracting from it, and we eventually write some new value to this balance. So essentially, at the point we realize that subtraction happens, that's already not good. That already means that with regard to this sender, we are not going to get that much out of sharding. So inevitably, if we want to run this transition, the shard will have to have an ownership for the sender, because subtraction is kind of tricky to make commutative, especially if there is also addition involved. But we still have hope for this other field, which is balances of 2. So it's component of the very same map as balances of sender. But this is something that at the end we see is only a subject of addition. So as the summary says, at the end, the only thing that has been done to the balances of 2 is to add a certain constant amount to it. And the balances of 2 has been used just once. So this is what the last gray rectangle in the bottom right corner says. And as you can see, this analysis is actually pretty simple. It's syntax driven. It's slightly more complicated in the presence of higher order functions, which Scylla has, but overall, it's not particularly difficult to engineer it and argue for its summaries. Okay, so the next stage happens after we get the summaries. And this stage has to do with turning those summaries with some additional user input into the set of sharding constraints. So sharding constraints are tricky things. So they are prescriptions for the nodes that are going to dispatch transaction based on which transition it executes to the corresponding shards. So for example, imagine that there is a transaction that executes this transfer, and it has a sender and it has a 2. So any shard that needs to execute this transaction must own the balances of sender, but it doesn't need to own balances of 2. So, and the nodes that will figure out how to forward this transaction to the corresponding shard, they will have to take these constraints into the account. So now let's see how we can obtain those constraints. So if we want to run this transaction on multiple shards, what constraints needs to be respected? So we take a look at these restrictions, and we see that because balances of sender is a subject of subtraction and also of conditioning, we actually need to, every shard that runs this transition needs to own this field. So there obviously might be at most one shard that has it. So that is a restriction. But on the other hand, this shard doesn't need to own balances of 2, because balances of 2 is a subject of addition with linearity preserved. So for that, we only need to, the only thing we need to know is what to do after we have incremented the balances over different shards. And this is where this idea of inferring the join strategy comes. So in the grammar on the top left, we have 2 different strategies to reconcile the changes in the contract state as a result of sharding. On overwrite means, well, the changes have been made uniquely by one shard. So this shard will just broadcast this the new state of this component that everyone will accept. The int merge says that, well, the changes were the subject of commutative addition. So we need to take the initial state obtained after executing all exclusive operations and add all the deltas. So this also comes with an interesting implication that we actually need to slightly weaken the semantics of the blockchain, meaning that the contract doesn't have access to the immediate state it would get after being transferred more money. So these balances of 2, it might have been implemented by shards different from yourself, but you would know it only after the next merge, after the next join happens. So this is actually a rather reasonable weakening. So this is reminiscent to what processors do with regard to bufferizing certain operations that have a benign effect, but this is something that I feel we have to emphasize. Anyway, so what happens next is now we know how to shard these transactions, or rather like how to dispatch this transaction based on these constraints. And this is where the main usage phase comes to the play. Okay, so that's something not interesting. So roughly what happened by now? So we haven't yet touched any blockchain-based executions. We only looked at the analyzer. And the pipeline of the analysis is follows. So we, before the deployment, the user, the contract developer, gives it a contract, and the contract derives the summaries for all transitions, such as read-write operations and linearity. So then, as a next thing, the user says, okay, you know, I actually want to deploy this contract and indicate that this set of transitions should be run in the most parallelizable way. Can you help me with that? So then we have what's called sharding query solver that takes these transitions and also some information of which reads are okay to consider weak. And with the summaries at hand, the second part of the analysis say, oh, these are the constraints that need to be respected when you dispatch those transactions. So that's actually, I'm pretty sure that's an NP-complete problem to compute those the optimal set of those constraints. But luckily, our summaries are not very large, so we just do it by sort of brute force with backtracking. And these constraints determine conditions that a shard needs to satisfy in order to run the transaction with this transition. So these conditions are actually something that then checked dynamically by the nodes that dispatch the transactions. So an obvious application of that is if you are greedy, if you want to shard more transactions, then luckily, due to their inherent interference, you are going to get more restrictive constraints. So if you have like the contract that I've had before that doubles and increments, our analysis will not give you a very useful sharding signature. It will basically say all those transitions needs to go to the same shard. And this shard should be the one that owns this contract's entire state. But if we say that, okay, we are okay with multiplications being processed by a dedicated shard, but the addition needs to be sharded and executed in parallel, then we can get something better. So that's essentially the analysis. And I'm going to spend a few more minutes just quickly outlining how it has been integrated. But maybe there are any questions at this point about the analysis intuition and what is it doing?
So one question that I have, and give me a second to formulate it quite precisely, is I imagine it might be the case that contracts might be written in a way that make them difficult to shard, right? And if the user could like rewrite the contract somehow, it would be easier to distribute properly. Could this help with that? Is there any way to give like hints back to the contract writer that, you know,
Perfect question. Perfect question. I have a slide about it in about which will be coming in about 5 minutes. So would you
okay,
mind?
well, I will delay that.
Yeah, but thank you. I'm very happy that this question has been asked. So now it justifies me putting that slide into the presentation. All right. All right. So integration. Well, okay, obviously, as any production system, Zilliqa is pretty complicated. That was a picture that we put into one of the early drafts. I think we are going to take it out because it scares everyone away. But it sort of shows that, well, you know, we have the charts like 1, 2, 3, and we also have this dedicated chart DS committee, directory service committee, that reconciles whatever cannot be processed in parallel. So the important part is that we have this lookup nodes on the left, and you can see this swarm of transactions ramming into them, and they are the guys who take care of putting those transactions into the corresponding chart. So those lookup nodes are those who validate the transactions with regard to the sharding constraints and tell them where to go. So how exactly we integrated CoSplit with Zilliqa? So the way it works is we run the static analysis upon the contract deployment. Whether it's a good idea in terms of performance, I will respond just in a minute. So then each contract gets a sharding signature, but this sharding signature actually requires input from the user. So I am welcoming suggestions because we don't know a better way to tell something good. Okay, so in principle, we could obviously run all subsets of, like try to analyze all subsets of conditions and figure out which one shards well. And this is not entirely unreasonable, given that this is something that would have been performed offline by the contract developer, but not by the validators of the blockchain. So it would not impose any transaction validation overhead. So, and then the transactions are being dispatched based on the signature that has been deployed as a metadata along with the contract, and they tell where the transactions need to go. So, and finally, as a part of signature, we also have these joint strategies that inform this DS, this ultimate committee, about how the state after performing commutative or disjoint operations need to be reconciled. And this joint strategies is something that we, we've ended up implementing just 2 of them, but obviously for any partial commutative associative operations, we can have one. It's just addition is so common that we settle on that, but obviously we could have one for multiplication and different combinators of those. Okay, evaluation. So we run the analysis as a part of the contract deployment, and it does add a sizable overhead, but overall it's not too bad comparing to the other mandatory phases that the miners do when they validate a contract deployed by someone. So here is a relative breakdown. So this is like 40 something all unique contracts deployed on Zilliqa from like real production blockchain. So we run it on all of them. So, and you can see that parsing, type checking, and sharding analysis, they roughly take the same amount, and it's always within milliseconds. So 6 milliseconds, it's worth for some pretty sizable contract. Okay, what's more interesting? Okay, so this is actually why, like, whether it was all worth it. So this is us taking some characteristic transitions of some popular contracts and trying to see if they can be sharded. So each of the groups of the bars is just one transition run in parallel. So assuming that everything else being processed sequentially by some dedicated shard. So the first 2 for the fungible token, and as you can see, transfer shards extremely well. Crowdfunding donates also shards very well. Non-fungible token, that's a more fancy version of a bank, which also stores collectible. So this is something that required us some interesting relaxation in the blockchain semantics, but we managed to get it, and we proved that it doesn't break anything. So that also gets linear speed up. So proof IPFS, that's actually something that doesn't shard that well. It gets a little bit of speed up for 3 shards, but then it degrades, but not too badly. So essentially, even with sharding, we don't get performance worse than with the baseline. So the reason why this one doesn't shard that well is that it actually requires ownership of 2 components of the state, whereas all other require exclusive ownership of just one. And well, then this significantly limits the flexibility in how you can choose shards. So basically, that's another bottleneck, and we might need to do something about. So UD stands for Unstoppable Domains. That's a rather curious application. So this is the most popular contract on the Zilliqa blockchain, just one of the early adopters, which amounts for like 70% of the entire traffic in the system to date. And well, as you can see, we also can do quite well for it. So obviously, this is an approach that works to some extent, and there are some limitations. So one limitation is something that Rupsha might have hinted with her question. So it's pretty difficult to do something for transactions that touch multiple contracts. Well, we are still positive that we can do it, but that just means that the dispatcher nodes will have to do significantly more validation. So they would have to validate the signatures with regard to multiple contracts. And at the moment, the sharding is static. So it means that upon contract deployment, we need to figure out what transitions are going to be sharded. And if those transitions are not going to be used as much as we expected, there's still going to be an overhead on dispatching them by the nodes in the correct shards. And this is something that is not so nice, but that would probably require significant changes in the protocol. So it would allow for dynamic reconfiguration of the sharding strategy. Future work. Okay, so we obviously want to leave this static sharding limitation and multiple contract transactions, but now also something that Ben wondered about. So when we were looking at those contracts, we actually ended up refactoring a couple of them just to make the point. So it turns out that the way people write these contracts, they kind of, for the human, it's apparent that this can be executed in parallel, but the implementations make it very, very obscure. Like, for example, one version of the transfer that we have seen. So it doesn't specify the owner. So it's a tricky transfer. It's transfer on behalf of someone. And on behalf of whom, that is something that is not given as a parameter to the transition, which make it very easy to check. At the dispatch, it's something that is retrieved as the very first line of the contract. And well, what we can do, we can make a semantic changing transformation of this transition, which would keep it more or less the same, but it would just expose slightly more information at the level of parameters. So the dispatcher nodes could validate that. So this is kind of part of the code that had to be rewritten, but it's very much mechanical. And with this signature of this transition, that actually becomes very much shardable. Whereas with this one, just because we need to uncover, like, we could make it shardable, but that would mean the nodes would essentially have to execute this transition rather than just checking some of its input parameters. And we thought that that wouldn't be right. It would be significant performance and also security issue. Okay, so now to conclude what I have shown to you. So I have shown you the problem, and the problem was that blockchains don't scale well. And if we want to introduce parallelism techniques for sharding, that also doesn't work so well for smart contracts. But still, we can use the ideas that are very much well understood in the compiler community and also in the concurrency community to recover some of this parallelism by means of doing the analysis that pessimistically tells us which parts of the contract can be run in parallel with which other parts of the contract. So with that, now having stated this problem, we hit it with known techniques for static analysis to soundly determine the opportunities for parallelism. And we integrated our solution into real-world production blockchain and showed that it is indeed useful for the smart contracts that people write. And this is all I have, and I'll be happy to take questions.
Well, it's all applied virtually for Ilya. I have a couple questions, but I'll open up the floor to other people first.
So I had a question related to Ben's, which was about the transactions that are being identified by the user to provide to this shard query solver, right? So is there some kind of feedback mechanism there for the user? For instance, what if the user is very pessimistic about what transactions to provide to be sharded and so on? I mean,
so the way it works is as follows. So I mean, you can imagine it as a interaction loop with the user. So you write your contract. You say, oh, wouldn't it be nice to run this subset of its transitions in parallel? And then the solver takes that as an extra input, does rumble, and gives you a set of constraints. And then, well, okay, there is no more feedback than that, but then you can look at those constraints and say, oh, look, this actually requires the shards to have these two to own these two separate components of a map. And the chances that these two components of a map will fall into the same shard by randomly, it's pretty slim. So maybe that's just not a good one. For example, also if you give something like this increment contract that we had here, and you ask it to shard both transitions, increment and double, it will tell you, sorry, the only way I can make it consistently is just to execute all these, both these transitions sequentially. So double increment. Then there will have this problem that due to concurrent artifacts, you can have either or because of the sequence. And the constraint that will manifest is saying that you need to own the field counter. So essentially, there will be just one shard that can modify this field, which is not nice. We actually might want to have multiple shards modifying the counter and then just merging their contributions, as would be the case in the case of increment. So in terms of user feedback, it's not that nice. So we certainly don't spell out all this implication in text. But yeah, that's it.
Yeah, so I mean, I was actually, so you're talking about some feedback in the context of, something that the user provides, which is actually not amenable to sharding. I was actually thinking, what if the user is super conservative and doesn't really give as many transitions as options even, right? So would there be a possibility to present to the user some templates or some kinds of conditions about the kinds of transitions that the user should consider providing?
This is a good point. Yes, I think so. So in fact, what we did for the evaluation in one of the versions of this on this fork is that we just ran this on all subsets of transitions, and we had some notion that okay, so I came up with a metric called sharding ratio, basically saying what does it mean for this strategy to be good? How many transitions does it allow in principle to run in parallel with not that many restrictions?
Right.
All right, thank you for the question.
So, are there any other questions? Okay, can you go to the future work slide? There was something here. I think it's the next one, right? I think you said something along the lines of, oh, I guess it's the previous one.
Yeah, there it is. This one?
No, wait, there was a point that I.
Which one? What was the
point? There was something along the lines, maybe go next, the previous slide before this. There was.
Okay.
Yep. Maybe it's limitations. Yeah, so this. I was trying to get a sense of what the solution to this first problem looks like. So you said there's no support for sharding multi-contract transactions. So this corresponds essentially to a transaction that touches multiple contracts. And here my mental model of a contract is like an object or something, right?
Actor. So actor is a right model.
Actor is a better right model. Okay.
Yeah.
Combine the signatures from multiple contracts.
Well, okay, you have a proxy contract. Your user sends a message to this proxy contract. The proxy contract forwards this to, I don't know, like a booking system. So you want to book both a hotel and an airplane tickets, and those two are two different databases, and you also have a reservation contract that interfaces between all of them. Yeah, so so that would be tricky because you want to make commutative or disjoint changes to a number of contracts. And now you would need to have that transaction essentially expose all this sequence of messages that it's going to emit in the process of its execution. And each of these messages needs to go and be validated by the dispatchers for the fact whether it fits the constraints.
So, So it seems like that in fact, the example you just gave seems like a really natural application of these sorts of transactions, right? Where you want to do something that requires coordination among multiple actors.
In a way. So I think it's a good example of a composite smart contract. By the way, Ruksha, I suggest you take notes in the light of the discussion that we had. I would argue that there's also an alternative way you can implement this logic. So you can just make the registry, the booking service to be a client-side software. and that would be their responsibility to liaise with two contracts that, from the perspective of blockchain, would be just two contracts in isolation.
I see. Oh, that's interesting, actually. No, I don't want to push on that anymore.
I do want
So,
to
yeah.
put my question a little bit more.
Okay.
So, I mean,
Okay.
so what is really the bottleneck? I mean, I understand it must be scalability in basically taking all the transactions, all possible transactions. So there's no user in the loop here. Taking all the transactions and then figuring out an optimal subset. I mean, you know, with the max sharding ratio that you referred to, and maybe have the user somehow, you know, confirm that it's fine, and then go for it, right? And by optimal, it means not only transitions that actually lend themselves to your analysis easily, but also that can be repaired to lend themselves to their analysis, to your analysis. Because this seems sort of, you know, arbitrarily conditioned on this set of transitions that the user provides.
Right. Well, okay. So the thing is that not necessarily, okay, so two different subsets of transition might not be equally well shardable. So for example, you can imagine like 5 transitions being all like increments, so shard really, really well. And then 2 other transitions being like an increment and multiplication, meaning like don't shard at all. So the size of the set is not a good metric. Yeah, let me try to understand.
No, yeah, size is definitely not the best metric. There has to be some kind of measure, right? Some kind of objective function they're trying to maximize.
Okay, so I have to admit we didn't put that much thought into that. I mean, like obviously that rings many bells, like to the extent that it sounds like register allocation problem to some extent. So how would we choose the right set that would play the nicest with? Okay, I honestly don't know. So that's why at this point we just assume that there will be user in the loop. Our goal is just to give it something that, give her something that is sound and let them use.
Yeah.
Also, you see, like even something that shards very well might not be the most popular one. So you might not actually, but it might interfere with something that shards slightly less well, but is more popular. So I am sort of convinced that there is some non-trivial insight coming from the user who should say like which transitions are expected to be more widely used and hence need to be optimized for parallelism.
Yeah, that's actually a valuable argument to have the user in the loop.
Yeah, but if you have some sort of metric on sort of the strength of solutions, you could imagine there are some solutions that are just going to be silly, right? And you could sort of iterate and sort of present a set to the user to sort of identify which one makes the most sense, right? So
yeah, I think so.
Yeah. Yeah, I mean, coming up with a good, if there is a possibility of coming up with a good metric, a reasonable metric, then yeah, there would be some interesting alternatives.
Yeah, or just like make the protocol in a way that it could dynamically change the signatures based or choose different set of signatures based on the history observed prior to that.
Yeah.
that would be very interesting. Yeah.
Yeah, PL plus systems. You see, like I wonder if
And crypto.
Yeah, I wonder if Suresh is around to endorse this this line of thinking, but I hope he is, even he's not present.
Yeah, he seems to have left now.
Yeah,
but he was there.
Okay. I'm sure he would endorse it. So, okay. On that note, if it's already after 1, and I know it's 1 a.m. where Ilya is, does anyone else have it? Yeah. So, if anyone else has it, does anyone else have any like last minute questions they want to ask or feedback? If not, I'm sure Ilya is happy to respond to email requests.
Absolutely. Thank you.
Yeah. So let's thank Ilya again. I mean, we really appreciate you coming and giving this talk.
Thank you.
Yeah, nice talk. Thanks, Ilya.
Thank you so much, guys. It's been my pleasure. And thank you for sticking around and asking all these questions. Enjoy your space trip, Jack. All right then.
Will do.
Yeah.
Thanks, Ilya. Thanks for staying up
Yep,
late
thanks again.
and giving
Yep.
this wonderful talk.
All right. Looking forward. So the only thing it could be better if I actually was in West Lafayette, but maybe that's for the next time.
Next time.
Next time, yes.
Yeah. All right.
You're always welcome.
Okay. Thank you. All right then.
All right. See you everyone next Friday. I believe it's going to be Krish presenting next time. I will send emails and we should be using the same link. Bye-bye.
Okay. Bye.
Very good. Bye, Pedro.
Good night, Ilya.